And hello, good afternoon, everybody. Welcome online, and welcome to week 6, unbelievably, of our lockdown bioinformatics. So, yes, it's week 6. It's day number 24, and we're still talking R. So we're picking up from where we left off last week. And at the end of last week, I was discussing kind of the fundamentals of R, the data structures and data types that we need to know about in R in order to be able to be productive and write decent code in that language. And that's what we're going to carry on with today. So we've got, I think, one more day of these real fundamentals, and then we're going to start to think about important third-party packages and things other than the base R that we've been looking at so far. So we've got, as I said, a few more data structures to really think about today. Particularly, we're going to talk briefly about factors, matrices, lists, and data frames, and then from tomorrow we will start to look at some packages. So we'll think about some important widely used packages that we're going to make use of ourselves. We'll maybe talk a little bit about Bioconductor this week as well. We'll have a look at some data visualization and just working with data generally using those kind of packages, and then we'll turn our attention to RNA-Seq data after a bit of that kind of exploratory stuff. Yes, a few other things to cover today before we can start to get slightly more advanced. Okay, so I'm going to start today, and let me turn off my picture. There we go, there's my RStudio session. Just going to hit save on my script just to make sure that we've saved what we're doing. So if you recall, on Friday we talked about some vector functions. So these functions like length and unique and rev and sort, which work with vectors to give you various things. The names mostly are self-explanatory in these cases. Where the names aren't self-explanatory, if we remember, we can run the help operator, which is question mark, and then the name of a function to find the what amounts to the man page of that particular function. So we can always find out what functions do if the name of the function isn't completely self-explanatory, or if the way to use that function isn't completely obvious. We also looked at different ways of merging information. So we looked at paste to pull together different, in this case, characters into a single character variable. So paste 0 to do that with no separators in between your two characters, for instance, or paste to introduce a space by default in between them, and then how paste works not just on single variables but also on vectors. So we looked at producing this vector here with the string chr followed by the first five integers. And then importantly, we looked at different ways of subsetting vectors, which is a very important operation. So we looked at using numerical subsetting to pull out particular elements of vectors by the number that they fall in that particular vector. So x square brackets 5 pulls the fifth element out of that particular vector. We also looked at subsetting vectors using vectors of logicals. So a vector of logicals that has the same length as the vector that you're trying to subset will subset according to the true values in that logical vector. And the natural extension from that then is to consider these relational operators, which allow you to construct those vectors of logicals by using relational operators and your data. So the example of that was x less than 5, where this is applying a logical operator to all of the data in our vector x, and figuring out which elements of our vector x are less than 5, and then subsetting based on that expression to give us back the elements of x that are lower than 5, which is an important thing to be able to know about and to be able to do. So that was last week. And then, so today we're on to day 24, and I'm going to start today by talking about factors. So, factors. Factors are data structures in R, and really they're just an extension of a vector. So actually, it's a data type similar to the ones that we've seen so far, so double and character. And so a vector can also be a factor in a similar way to the way that a vector can also be a double. The important thing about factors is it's a way of encoding categorical data. So all of the elements in a factor belong to a predefined set of values, which are called levels. And factors have lots of uses in R. They generally crop up in when we're doing model fitting, and you're fitting against a categorical variable, that variable is almost always encoded as a factor to allow it to assume particular levels, and for R to be able to understand that data can only assume particular levels. Factors are also used often in plotting functions. So for instance, when you're colouring in the points on a scatter plot by particular variables, in order that your plotting function knows that those colours can only take certain values, factors are used because they're categorical, and the levels that a factor is able to take are predefined. So just to show you how this works, we're going to construct a character vector. I'm just going to type this out as effectively as a literal vector. Let's do this as an example. Just a few. This is the UCSC naming convention for chromosomes in the human genome. So this is a set of characters which crops up relatively regularly. I'm just going to do a subset of them, not all of them, because otherwise it's a lot of typing. Okay, so here we are. List of chromosome names, relatively short list. So just again a reminder, if we type in the name of the variable at the console, R will print that variable back out for us. So there we are. That's the list of chromosome names that I encoded in that vector. So this is a character vector. So is.character chrvec will return true because it's character and it's a vector. So is.vector will also return true. It's not yet a factor. We've not encoded it as a factor yet. So at the moment, with this as a character, if we sort this character vector, what you will find is that That's weird. What did I do? Oh, I meant that last one should be. So I shouldn't have two instances of chromosome 2. We should have an instance of chromosome 10. Sorry. I apologise. So I'll just edit that. Sorry. If you sort that character vector as it currently exists, so this is an alphabetical sort. So the natural sorting order of character data types in R is alphabetically. So as we discussed at the end on Friday, looking at the ASCII value of the characters in the strings here. So CHR1 sorts to the front, but then CHR10 sorts next, because alphanumerically CHR10 comes after CHR1, and then CHR2 comes after CHR10, because the 1 sorts before the 2, and that's kind of your paramount order. So the sort here is ordering based on the character value rather than numerically. But if this was a factor rather than a character, then R would sort it on the order of its levels rather than on the alphabetical order. So the natural ordering of a character is of a factor is different to that of a character. So if we give this, so let's create something different. Let's create a vector in a character vector in the order that we want it. Okay, so in this time we're going to have an ordered vector, and we're going to use paste 0 for this. So we used paste 0 last week. Okay, we're going to stick CHR in front of everything, and then we want if we're going to create all of the human chromosomes, we're going to do all the human chromosomes this time. So we're going to do 1 to 22. We've seen this colon operator for doing consecutive numbers before, and then the three chromosomes with letter names X, Y, and M. And importantly here, we're creating this in the order that we want them to be sorted. So unlike this one from before, this isn't the order in which we would want it to be sorted. And sort doesn't resolve that for us, whereas this is in the order, the correct order. But again, if we try to sort this as it currently is, so this is a character vector now, ordered vec is a character vector. It's in the order we want, but its natural sorting order is still alphabetical, because it's still a character vector. So again, if we sort it, character 10, 11, 12, etc. sort after character 1, sort after CHR1, but before CHR2, because that's the alphabetical order. But if we use this character vector to make a factor, okay, so we're going to make a CHR, so character factor, using the function factor. So a factor is made by using the function factor. We've got our what we're gonna do is we're gonna pass this. We're gonna make a factor out of this vector that we used before, the CHR3, CHRX, etc. factor. So we're going to turn that character vector into a factor. The levels that is possible for this factor to take are defined by this vector that we created here on the line above, this ordered vector. And by default, R would resort this in alphabetical order, so we need to tell R that this is ordered in the way that we want it to be ordered. And so to do that, we need to give R an extra argument, which is ordered equals true. Okay. What I'm going to start to do actually at this point, because what you'll notice is quite often my lines of code are just slipping off the right hand side of the screen, even if it's only by a character or two, and I want you to be able to see the full commands. R lets you split commands over multiple lines. So if you've opened a bracket, you can have your command split over multiple lines until the bracket closes, and R will be able to interpret that. So I'm going to split this factor function call over 3 lines. And the convention is to do this after each argument. So the arguments are separated by commas. So after each argument, we're going to put a comma in. Okay, so I'm just putting line breaks in just to make this easier to read and to make sure that you can see it all on one line. So what this will do is this will create a factor. That's what the function call is doing. It's creating a factor based on this character vector, which we can see up here, which again I'm just going to split over more than one line just so you can see the whole vector. All of the levels that this factor can possibly take are defined by this vector, which we've created here, which has all of our what we're going to assume are chromosome names in the right order, and we're telling R that that's the order that we want. We don't want it to try and reorder it into alphabetical order or anything like that. We want it to maintain the order that we've told it. So we've set ordered equal to true. And so this will create our first factor. Okay. And if we have a look at that factor, we will see that it differs slightly from the character vector that contains the same data. So if we print out the vector, we can see that we just get back the vector as we expect to get it. Each entry in the vector presented separately as a separate entry. The factor looks slightly different. The characters themselves aren't in quotes, and that's telling you something about this, that we've got what are obviously character elements, but they're not in quotes. But also we've got the levels defined. So this is telling us that this factor is able to take 25 different levels, and that those levels have an order. That chromosome 1, CHR1 is less than CHR2 is less than CHR3, etc. So now, when we sort our factor rather than our vector, sort CHR fac, it will sort in the order that we expect. And that's because we've defined the sort ordering when we've defined the factor. So CHR1, CHR2, etc. Are defined in the way that we've defined the factor. So this can be very useful in various ways, which we will come across later on. So again, it's one of these things where we're kind of storing up knowledge here to look at later. Factors are important. So for instance, when we define our the design of our RNA-Seq experiment, when we're loading that RNA-Seq experiment in for analysis, we define the different categories of experimental variable as factors, so that R can understand that our experiment only has particular levels contained within it, and will analyse those appropriately. So factors again will be important when we come back to these things later. Okay, so that's factors. The next thing that I want to talk about are matrices. I'm just gonna divert myself slightly because there's an interesting question in the live comments, which is, do single quotes and double quotes matter in R? It doesn't matter. Single quotes and double quotes are pretty much interchangeable. If you want quotes inside your string, so if you want things like apostrophes inside your strings, then a double quote can contain a single quote. like that. But if you wrapped this in single quotes, then things would get quite broken. So there's that to a certain extent. Otherwise, as far as I can tell, most of the time, single quotes and double quotes really doesn't matter. I'm really bad at consistency on that, and I do, as you can see, really even in this single page of code that I've got on the screen right now, you can see that I use them almost entirely interchangeably all of the time. There are probably style guides kicking around that tell you which is preferred, but I don't tend to. I never even give it a thought when I'm typing. To be honest, I just use whichever comes into my brain, or whichever my muscle memory tells me is the right one to use at that time. So even within constructing ordered vec here, I've used single quotes and double quotes. I apologise for that, it's very inconsistent of me. But in the majority of cases, it doesn't make any difference in R. Okay. Right. Matrices, so that's what's next. So far, all of the data structures that we've looked at in R are one-dimensional. So vectors, particularly, a vector is a one-dimensional data structure. It has length, but it doesn't have width, for instance. And the matrix is our first opportunity to see a two-dimensional data structure in R. So a matrix is essentially a vector, but it has two additional attributes to a vector. So a vector has length, and obviously its contents. A matrix has its contents and has a length as well, but a matrix also has a number of rows and a number of columns, which are defined by R as with n row and n col. And this describes not just the contents of the matrix, but also the shape of the matrix. So like factor, we have a function that we can use to construct a matrix. And there's no prizes for guesses. So actually, like vector as well, the function for constructing a vector is C. The function for constructing a factor is factor. And the function for constructing a matrix is matrix. Okay? So delete those. So to construct a matrix, my first matrix, you give your matrix some contents, and like a factor, a matrix can only contain a single data type. So your matrix is either going to be a matrix of doubles, or a matrix of characters, or a matrix of logicals. It's not going to contain multiple types of data. So in this instance here, we're going to put some numbers into our matrix. So the numbers 1 to 12. And then it needs two additional pieces of information. So unlike constructing a vector, where you really just need to give it the contents, when you construct a matrix, you need to give it two additional pieces of information. That's the number of rows, so n row, and we're going to construct our matrix here with 4 rows, and a number of columns, n col, and we're going to construct this matrix with 3 columns. And the number of rows multiplied by the number of columns must come to the length of the data. So in this case, we've got 12 individual data points, so the numbers 1 through 12, and we've got 4 rows and 3 columns, and 4 times 3 is 12. So our data, the data that we're putting into our matrix fits into the matrix. And by default, R will fill up a matrix by column-wise, so it will fill column by column, which we'll see when we've constructed this matrix. So we'll put the first 4 values. In this case, we've got 4 rows and 3 columns, so it will fill up the first column first. So the 4 entries in the first column, because we've got 4 rows. So we'll put the numbers 1 through 4 in the first column, and then it will go on to the second column, and then it will go on to the third column. I don't actually know what will happen if you don't give it enough data, and we can experiment with that in just a second. So that's our first matrix. So as I said before, this has more than one. This has 2 dimensions. So unlike a vector, where we will just get back the list of the numbers that we put in, with a matrix you'll see that the results are slightly different. So there we go. There's our matrix. So the matrix now has rows down the left-hand side. These are the determinants for the row, and across the top we've got the columns. So we've got 3 columns, 1, 2, and 3, and 4 rows, 1, 2, 3, and 4. And as I said when I was describing this, the data goes into the matrix column-wise. So the first 4 values go into the first column, the second 4 go into the second column, and the third 4 go into the third column. If you want to fill it up row-wise, which you can do, then you would define, instead of just doing this, you would pass an extra argument. So let's just have a look at this. We won't capture this as a variable, but let's have a look. You would say by row equals true. So by default, by row is false. So this will, instead of entering the data in column-wise, this will enter the data in row-wise. So instead of being 1, 5, 9, the first row will be 1, 2, 3. Like that. Okay? So that puts the data in row-wise, which is useful to know because sometimes that's going to be the way around your data is. Okay, let's just one other test because I don't know the answer. Let's see what happens if we don't give the call to matrix enough data. So let's give it 6 observations rather than 12 observations. So we're putting these 6 observations into a matrix which has 12 available slots, for want of a better word. Okay, so we're seeing vector recycling. So it's filled up the 12 values and it's done it by reusing that vector. So it got to the end of we went 1, 2, 3, 4, then 5, 6. We got to the end of the vector that was given to matrix, and so it reused that vector and carried on filling in our matrix. So it didn't fill it up with NAs, and it didn't complain that the data that you're giving it doesn't fit into the matrix. It's recycled the vector and filled up the matrix by recycling the vector. Okay, so that's useful to know as well. So this is a matrix, and lots of arithmetic in R is done on matrices. So it's an extremely useful data structure to know about. As with a vector, it can't contain more than one type of data. So if we put a character in to our matrix, so let's add an additional thing in there and add a character into our matrix. There you go. It complains that that's complaining about something else entirely. Let's give it 6 things, and there you go. So it does now fit into the matrix, but it's now a character matrix. So even though I gave it 5 numbers and a character, it's converted them all into characters in exactly the same way as it would do if we constructed a vector like this. So we've learned 2 things there. One, the first thing is that our matrix can only contain one type of value. And the other thing is that if your data doesn't divide nicely into your matrix, even if it's by multiplying it, if that makes sense, then R will refuse to construct your matrix. So there we had 7 observations and a matrix that could contain 12 observations, and R refused to create the matrix for us. So that's a useful thing to know as well. Okay, so to go back to my first matrix, which we created on line 153 here, there are some functions which are useful to be able to use with matrices, to know about. Oh, thanks, Pia. You're right. It's a warning, not an error. Yes. Sorry. Thank you, Pia. Peter's correct in the comments. Yes, it's not refused to create the matrix at all. It has created the matrix. The matrix is there. It's just warned you that the data doesn't fit into the matrix. Thanks for pointing that out. It's a very good point. So it is still a character matrix. It's still recycled the vector that you've given it, but it has warned that it doesn't fit into the matrix neatly. But it has still created the matrix, so that's a very good point to note. Okay, thanks, Peter, for that. Okay, so functions that we can use with matrices. So a couple that I want to point out. The first one is, okay, so like for vectors we have length. So if you remember, length x tells me how many elements there are in my vector, where x is my vector. I'm pretty sure length will actually work with a matrix. And it will tell you how many things there are in your matrix. So the length of our matrix, without thinking about the dimensions of it, is 12, because it has 12 elements. But if we do want to know what the dimensions are, then dim will tell us that. So the dim of my matrix, or the dimensions of my matrix, tells me, first of all, how many rows there are. So R always deals with the rows first and the columns second. And that's a really important thing to remember, is that when you ask about dimensions, the thing that comes back first is always the rows. And this is true wherever you're dealing with rows and columns in R. The rows are first and the columns are second. Okay, so that's really important. So the results of this call to the dim function here is that our matrix has 4 rows and 3 columns. 2 more things. One is the transpose function, which is t. So you transpose a matrix with the t function. So that gives you the transposition of the matrix. So where my first matrix looks like that, with 4 rows, 3 columns, 1, 2, 3, 4 in the first column. The transposition of that has 4 columns and 3 rows, and 1, 2, 3, 4 is in the first row. So the columns here have become the rows here. So that's the transposition of the matrix. So the function t is how you transpose a matrix. And then finally, you can flatten your matrix. So you can return your matrix to a one-dimensional data structure, and you can do that with as.vector. And as the constructor of matrix puts values into your matrix effectively in the order you put them in. So this is a vector containing the data that's inside my matrix, and it's pulled it out column-wise. So bear in mind that all of these, so things like this transformation, this T transformation that we've done here, the transposition, that didn't change our data structure that we've saved in memory at all. So running that transposition, it printed out the transposed matrix, but it didn't save it. Okay, my first matrix in memory is still the untransposed version with 4 rows and 3 columns. So the transposition here has printed it out onto the screen, what we can think of as standard output, I guess. But it hasn't changed that data structure in memory. So when we do as vector on my first matrix, the data is still in the columns it was when we put it in, so it extracts it quite happily. If we saved the results of my first vector, so T matrix saved as the transposition of my first matrix. So now we've saved that matrix as a new variable, and we can, if we then flatten that T matrix, it will still, my prediction is at least, it will still extract the data column-wise, so the results, there you go, will be quite different because the matrix is different. It's been transposed, so the data that's in the columns is different because the columns now are what the rows were before. So when you extract that data back out of that transposed matrix, the order is different because the matrix has been transposed. So these are all little things, and I'm aware that at the moment this is all very kind of noddy example driven. It's like here's some trivial data and here's some transformations that won't necessarily make a huge amount of sense to you until later. But again, I think it's important to lay these ideas out on the table early on so that we can refer back to them. Okay, that's an interesting question, which we can find out by experiment. Is by row equals true saved in the matrix so that the vector reads it back out so that by as.vector reads it back out like that? I suspect that isn't true. So let's see. So here we go. My second vector is going to be the by row vector. There we go. Which, if you remember, looks like that. So the data's filled up in the rows now. So again, this is different to the transposed matrix, but the data's been filled into the rows rather than into the columns. I rather suspect that as.vector, sorry, put this in the script, my second vector, the results will be as you expect. You'll get 1, 4, 7, 2, 5, 11, etc. Okay, so yeah, so it's still pulling the data out column-wise. So let's see. Question mark, my second vector. No, that's not what it's to do. Sorry. As vector. So there may be a way with as vector of pulling the data out row-wise rather than column-wise. But actually it doesn't look like it. No, it doesn't look like it. So as vector is always going to flatten in a column-wise way, judging by this help file. So yes, the fact that you constructed your matrix, I don't know why I called this a vector, because my brain's not working clearly on a Monday afternoon. The fact that you constructed this matrix by row is not, that fact is not saved in the matrix, because the matrix is a very straightforward data structure, and it doesn't allow you to encode any of this additional information alongside it. We will look at more complicated data structures later, which would allow you to do that. would the transposition work? Let's have a look. Let's transpose it and see. Yeah, the transposition does work. So that gets you back out. So yeah, if you fill in row-wise, then you'd have to remember to transpose to get it back row-wise as a flat vector. Okay, so that is matrices. So we've got two more data structures to talk about today. One of them is effectively a one-dimensional data structure, although actually it can be multi-dimensional. And then the final one is the kind of the two-dimensional analogy of it. So first of all is lists. Okay, so a list, unlike a vector, can contain objects of different data types. So in a vector, all of the objects inside your vector must have the same type, and if they don't have the same type, then they will be changed to make sure that they do. And that isn't true of a list. A list can contain multiple data types in a single construct. So, for example, let's use let's do a list that contains some information about a gene. Okay, so list. So a gene can have a name. DH. What else can a gene have? Whether or not it's protein coding. Is it a protein coding gene? So in this case, that's true. Okay, so this time in our list, the first piece of information is a character, and the second piece of information is a logical. Now, if this was a vector, then the logical would be converted into a character. It would become the string true. But in a list, that isn't going to happen. What other information can we have about a gene? We can have the chromosome, which it is encoded on. Okay, GAPDH is on chromosome 13. So there you go, there's another piece of information. And this time we've encoded the chromosome as a double, as a number. This is now, we've got 3 different data types in this list. And again, if this was a vector, these things would all be encoded as characters because one of them is a character. So everything else would be changed to be a character. In a list, this is not true. This isn't the case. All of these things will keep their own type. So let's create our list called gene. There you go. So again, the constructor for a list is a function called list. Okay, so here we go. Gene now looks like this. So a list looks quite different to a vector, or even a matrix. It's again a very different data structure. So a list consists of multiple elements. Each of those elements, in the way that it's printed out here, is preceded by a $sign. So we have the name element, which contains, this is actually a vector. It's a vector with a single element, but it's a character vector. Okay, so the name contains a single character. The protein coding bit contains a logical, and the chromosome bit contains a double. So these are all maintained their type. Within each of these, I could, if I wanted to, put a vector of characters under name, but they would all have to be characters. So within each individual element of the list, the data type has to be the same. I forgot to talk about extracting values from matrices. Oh, I'll come back to that in a second. Right, so we can extract values back out of a list, and we can do that in a number of ways. So if you remember, for vectors, so our vector x, we could extract the first element of the vector x using this square bracket notation with a 1 in it, or with a number in it, for example. And this would extract the first element of our vector x. We can do a similar thing with a list, but in order to extract the first element of a list, you need 2 square brackets, which looks really odd. I don't like this particularly, but it is the way it is. So if we want to extract the first element of our list, we would have 2 square brackets and then a 1 inside those two, inside the inner of those 2 square brackets, and this will extract the first element of our list. We can also, in this instance, do it by name, because we've given the elements of our list names. So we've called them name, protein coding, and chromosome. So we can do gene, square bracket, quotes, name, to extract the name element from our list. You can also do it using this dollars character. So gene, sorry, do it in the script. Gene dollars name, this time no quotes, just to really confuse you, will also extract that element from that list. So these 3 things on lines 178, 179 and 180 are all interchangeable. They're all doing the same thing. They're extracting the first element from this list, but they're doing it in different ways. This dollars notation we will come back to shortly, because we use it for other things, so it's useful to know. So these are different ways of extracting elements from your list. I should have mentioned ways of extracting from matrices as well. So we've got my first matrix back here, which has these elements. If we want a subset of this, we extracted a slightly different way to vectors and even lists. It's still square brackets for extracting elements, but with a matrix, because you've got 2 dimensions, you need to have 2 dimensions in your extraction code as well. So in order to get some elements out of your matrix, so say we want the 3rd and the 4th row, and we want the 2nd and the 3rd column, we have a comma inside our square brackets here. The expression before the comma is telling R which rows you want. So here we're saying I want the 3rd and the 4th row from this matrix. The expression after the comma is telling R which columns you want. So here the 2nd and 3rd columns. So this will extract that slice of our matrix. Okay, so that's the way that we would extract from a matrix. So you need to preserve the dimensions by using a comma inside your square brackets. And as I've already mentioned this afternoon, R always deals with the rows first and the columns second. So the rows go before the comma and the columns go after the comma. You could equally do this with a vector of booleans, like a vector of logicals, like we've done before. So like we were doing with vectors, if you had before the comma true, false, true, false, then a comma. So this will give me back the first row and the third row, but not the second and the fourth because they're false. If you leave either expression before or after the comma, if you leave them empty, then R will return you all of that dimension. So if I leave the expression after the comma empty, then R will give me back all of the columns because I'm not filtering the columns at all by doing that. So there you go, that's given me back the first and the third rows of the matrix and all of the columns. So it's excluded the second and the fourth row because of this vector of logicals that I've passed in as an expression for filtering. So filtering a matrix works in a very similar way to filtering a vector. And you can construct these vectors of logicals in exactly the same way as we were doing. So you could say my first matrix let me think. Actually, let's come back to that because that's going to get a bit complicated. Okay, so but you can come up with expressions which construct those vectors of logicals as well in order to do the filtering. We'll look at that in more detail another time. I'm not going to do it now because I'm aware that time is running short. Okay, so we can subset these data sets in similar ways. We can do the same with lists as well. So the final thing I want to talk about today is data frames. So a data frame is the primary way in which base R encodes tables of data. So a data frame has features similar to a matrix because it's a two-dimensional structure, but also similar to a list in that it can contain multiple types of data. So a data frame can contain, is effectively a table. Okay, so it can contain, again, multiple rows, multiple columns, and each of those rows and columns, each of those rows can contain multiple different types of data. Each column in a data frame is effectively a vector. So each column in a data frame has to contain the same type of information. And if it doesn't, then the same typecasting will happen within a column as happens with a vector. So data frames. Okay, so constructed with the method, with the function data.frame, which is a little bit odd because it's got a dot in the name of the function. This does crop up in R quite a lot. This would look very strange in other programming languages where the dot means something. So in Python, the dot is a meaningful character and you can't use it in function names, but you do in R because R is weird. Right, okay, so let's construct a data frame of some example data. So you construct it like a list. So each element of your data frame, each column of your data frame has a name. So we're going to have a column which has gene symbol as the name. And let's put three things in here. So let's put in TP53. Let's put in genes. I know they're not made up, but you know what I mean. I'm going to split this across multiple lines. So I'm going to put the comma and then a new line symbol. So I'm going to split this across multiple lines to make it easier to read. So that's our first column. So each argument that you pass to your data frame function is a column in the resulting data frame. So here we're creating a column called gene symbol, which has 3 entries. So now that our first column has 3 entries, all of our subsequent columns must also have 3 entries. Otherwise, R will behave oddly. Now, whether it will refuse to create it or not remains to be seen. I'm not going to experiment with that today. But so let's create another column. So let's have a column for fold change. Okay. Here's a second column. It's going to be a vector again. It's got to have 3 values in it. So let's have, it doesn't really matter what they are, so 3 numbers. And 4. Right, okay, so 3 numbers, because this column has to have the same number as observations as the first column. In this case, they're numeric. So then we will have our 2 more columns, sorry. We will have a p value column, which again is going to be a vector of numerics. So let's have some numbers in here. Okay, so 3 values in this column to match the others, and then finally we're going to have a vector of logicals to say whether or not these observations are significant. So true, true, and false. Okay. So this will create a 2-dimensional data structure, which will have 4 columns. Sorry, because that's what each of my arguments here becomes a column, and each of those columns will have 3 rows because each of my vectors here has 3 observations in it. So this will make a 3-row by 4-column data frame. So after because each one of these is an argument, after each argument you get the argument name equals, and then the argument value, and then you get a comma, because arguments are comma separated. So argument name equals argument value, and then a comma to move on to the next argument. And then argument name equals argument value, and then a comma. And then the last one, argument name equals argument value. And this time it's the last one, so no comma after it, no trailing comma, and we close the bracket. This bracket here is closing the bracket that we opened at the beginning of the data frame up here. And you'll notice that RStudio is showing me that. So when my cursor is after this bracket, the bracket that it's paired with is highlighted by RStudio in this grey colour. So this grey colour is showing me that this bracket here is the pair of this bracket here. And if I move my cursor 1 place to the left, the highlighting will change to show me that this bracket here, just in front of my cursor, is the pair of this bracket at the beginning of the construction of this vector. So this is RStudio telling me about the construction of my code. You may also have noticed that when you highlight an element in your code, so if I highlight gene here, RStudio highlights for me all the other occurrences of that element. So of that, in this case, of this variable, so this variable gene is reused in my code in these places. This is RStudio trying to help me out, trying to show me useful and informative things about the code that I have written. Okay, so we've constructed this data frame using this function, this data frame function with these 4 arguments. So now our data frame looks like this. So as predicted, it has 4 columns. So the gene symbol column, the fold change column, the p-value column, and the significant column. And each of those columns has 3 rows, with the observations in the order in which we put them in our constructor here, the way that we built our data frame. So that's a data frame. and our data frame is analogous to, in fact, it's a special type of list. So we can extract data from our data frame in the same way as we extracted data from our list. So we can see just above here, we extracted the elements of our list using square brackets and using using the dollar sign and things like that. So we can extract an element from our data frame using the double square brackets notation. So 2 square brackets, and then the name of one of our columns of data. So one of the arguments that we fed in. So fold underscore change will give me back the fold change column. We can also use, and it's more common to use, what's called the dollars operator or the string operator. So df, then a dollar, and our studio here is clever, and it's giving me suggestions for the columns that are present in my data frame. So I can use the arrow keys to navigate these and then press enter to pick one, or I can use the mouse to point at them and click to pick one. So I'm going to pick gene symbol here. Okay, so df dollars gene symbol will give me back the gene symbol column from my data frame. So let's do that. So there you go, there's my gene symbol column presented back to me as the contents of that column. It's important to note here that the gene symbol column, we put it in as a character vector. It's been saved in our data frame as a factor. So what R is giving us back here in df when I retrieve the gene symbol column is not a character vector, it's a factor, and that is an important and extremely trippy-uppery feature of R. That when you create a data frame like this in R 3.6, which is the version of R that we're all using, by default, R will convert character vectors to factors. There's an argument for data frame, which is, let me put it into this call here. So I'm going to put a comma and then enter. So this is allowing me to enter a new argument, an argument of data frame, which is known as strings as factors. Okay, whether this is true or false determines whether R creates character columns as characters or as factors. And by default, in R 3.6, which is the version of R that I'm using here, strings as factors is true. If you want the alternative behavior, you have to set strings as factors equal to false. I should note that R version 4, which was released on Friday last week, this behavior has changed. So in R version 4, strings as factors is true by default. So in the data frame that we created in a couple of seconds ago, in R version 4, this would have been a character vector, not a factor, because that default behavior has changed in R version 4. So let's create this with strings as factors equals false, and then rerun our df dollars gene symbol line, and you will see now that this is indeed now a character vector. That's really important behavior to be aware of, and we'll come back to it another time. But it is now the default behavior in R version 4 that strings as factors is false. Okay, so that kind of brings us back to factors, and we've kind of gone full circle today. So we've talked about factors, we've talked about matrices, we've talked about lists, and we've talked about data frames. And that's the point at which I'm going to wrap up. Okay, so just going to quickly, there's just one comment I can quickly address at the end here. Is df square bracket 2 the same as df fold change? Yes, absolutely. The behavior is the same as it is for a list. So if you put a number in your double square brackets, it will retrieve the number of that column. So that behavior is absolutely the same. Okay, so I'm going to wrap up because I'm aware that I've gone on for longer than I have ever gone on before. It's 5:05, so in the UK at least. So I'm going to stop. So thanks everyone for tuning in. That's the last of these. I think anyway, the last of these really procedural. Let's just demonstrate a load of example stuff in R lessons. I think as of tomorrow, I'm going to try and move on to do some slightly more interesting things. Okay, so I will sign off without further ado. Thanks all for tuning in. I hope everybody's well, and I will speak to you all tomorrow. Farewell, goodbye.